Hello everyone, we're Group 9 and we're excited to present our senior design project, PAWS, Protected Access for Whiskered Subjects and AI-Assisted Litter Box System. This is our team. I'm Luana Capel, Photonic Science and Engineering. We have Kinza Rashid, Computer Engineering, Jeffrey Sotelo, Electrical Engineering, and Christian Williams, Computer Engineering. I took on this project because of our shared love of pets. However, if you own any yourself, you know how hard it is to maintain a clean space when animals are involved, especially when that includes different species. You may be aware one main issue with mixed pet households is that dogs are attracted to the smell of litter. Inevitably, they will sift through the litter, creating a health hazard for the dog and everyone else in the home. With our project, we wish to keep every pet healthy and maintain a cleaner home by developing a system that only allows cats inside the litter box. Our main goals include to create a physical enclosure where a regular litter box will be placed and blends well within the home, a motorized door for the cat to enter the enclosure, object detection that will identify if a cat is at the entrance, and finally, live feedback for the owner. To accomplish these goals, we have set objectives for each. For the first goal, we will build a wooden box with a top-mounted hinge that will offer quick access. For the door, we are designing a linear railing system powered by a stepper motor that will quickly open for the cat with sensors along the opening as safety measure. Next, we have machine learning algorithms to provide accurate object and identification, specifically to identify the cat at least 75% of the time. Lastly, we want the user to be updated of their pet's movements, so we plan on having a mobile app that will send push notifications whenever the cat enters, as well as recording pictures and activity logs throughout the day. These tables show the engineering specifications for electrical and optical components of PAWS, with the key specs highlighted. The most important part of our system will be the accurate identification of the cat and the motor reliability because we want to ensure the cat can enter the enclosure with ease. For the optical specs, the FOV or field of view will be key for the proximity sensor because we want to ensure enough area is being covered for the accurate detection. Here we have the whole system engineering requirements for PAWS. And our three main demonstratables are cat identification accuracy of at least 75%, Raspberry Pi response in less than 3 seconds, and we want the door to open or close in less than 8 seconds. Let's take a look at our physical enclosure. We want it to look like any other piece of furniture with a small opening as the entrance for the cat and an access door for easy cleaning. Our plans include caster wheels so that the box is easily movable, but they do have brakes so that safety is not a concern when the cat is inside the enclosure. Here's an inside look of PAWS. This is a rough estimate of where we will be placing all of our components. To account for the curious nature of cats, we do plan on 3D printing housing for everything. Here is the stepper motor attached to the threaded rod with the clamp and plexiglass door. These here are micro switches which will alert the system of when to stop the motor. Here is the intended location for the brake beam sensor PCB, and here is the main PCB with the power supply. Here's a look at our hardware block. PAWS is comprised of 5 subsystems: the main PCB, the Raspberry Pi, the optics, the linear railing system, and power.
Here's our software block diagram. This shows the basic functions inside each of our MSP430, Raspberry Pi, and mobile app components. It also shows when the parts will need to integrate with each other. Communication between the MSP and the Pi will use UART, and communication between the Pi and the mobile app is currently planned to use Wi-Fi.
Here we have the proximity sensor design. On the left, we have the PCB schematic with the lens and a cat to illustrate our goals for PAWS. The proximity sensor will be the starting point for the box, which when triggered will send a signal to the MCU and kickstart the process of identification. Because we need to detect the greater area at the entrance of our enclosure, a single lens designed to widen the acceptance angle will be placed in front of the photodetector to collect the infrared rays. The break-in sensor is a safety measure that will prevent the door from closing on the cat while they are still in the path of the railing system. Here you can see the schematics for the two boards which will be mounted on either side of the door frame.
A simple yet effective way to add an extra layer of safety and convenience to the system is with a pressure pad sensor placed at the entrance of the cat door. It ensures the cat is fully inside before the door is closed and also opens the door once the cat wishes to exit the enclosure. We compared two different force technologies and chose Velostat, a pressure-sensitive semiconductive material that decreases in resistance when pressure is applied. This works for our project because it is compatible with the MSP430 and fits our power requirements.
After comparing two linear rail systems, we picked the lead screw design. It can carry heavier loads at higher precision and repeatability. The plexiglass door will move with a drive nut along the threaded rod, giving the cat access to the enclosure.
For the motor selection process of our project, we started with considering both AC and DC motors, but early on in our research, all AC and specifically the brushed DC motors were ruled out. After comparing our final three DC motor options, the stepper motor technology was chosen for its precise position control, high holding torque, and low cost. The stepper motor is responsible for allowing access through the cat door and will need to reliably move the plexiglass sheet. To determine the best stepper motor, we evaluated four standard NEMA motors. This NEMA 17 model was chosen due to its reasonable holding torque and lower cost. It also operates at a voltage and rated current that is suitable for our project. We compared 5 different microcontroller technologies for our project. After ruling out the STM and ATmega chip technologies early on in our research and narrowing down our options to the remaining 3, we chose the MSP430, a 16-bit RISC microcontroller known for its ultra-low power consumption, mature development tools, and low cost. We evaluated 2 different MSP430 models. Since our processing tasks are light, controlling a motor, handling sensor data, and exchanging occasional UART messages, there's no need for extra memory or advanced features. Given this, the G2553 meets all of our project needs.
To handle PAWS machine learning tasks, we needed to choose between a physical single-board computer or an online cloud-based computing platform. We ended up choosing to buy an SBC, with the main factors in the decision being the budget and latency. Here we have a table comparing our main SBC options. The most important factors we're looking for are the price at the time of purchase, availability and shipping times, processing capabilities, which includes the CPU, GPU, and RAM, networking for the mobile app integration either through Wi-Fi or Bluetooth, and a general ease of setting up and usage. For the project's machine learning tasks, we ended up choosing the Raspberry Pi 5. The Pi 5 is one of the most affordable options we had at $60 for the 4GB version. It's widely available at most major retailers and is easily powerful enough to handle our necessary object detection and classification tasks. It's also extremely easy to set up, since you just need to insert a microSD card with the Raspberry Pi OS pre-installed. The Pi 5 has both Wi-Fi and Bluetooth capabilities for our mobile app, as well as dedicated GPIO pins for UART communication with the MSP430. As an added bonus, it has native support for the Raspberry Pi Camera Module 3, which is our chosen camera module.
In our project, selecting the right voltage regulator is crucial to ensure stable power delivery while maintaining efficiency and reliability. The following table shows different regulators and the main determinants we pulled from their respective datasheets. Our requirements include a 12-volt input, output voltages of 3.3 volts, 5 volts, and 5.2 volts, and a max output current range of 1 amp up to 5 amps. After careful evaluation, we determined that the MP1479 is the best fit that meets our specifications for our 1 amp current needs. It offers high-frequency switching capability, which allows for a compact PCB layout. Its cost-effectiveness also makes it an ideal choice for meeting power demands. Additionally, we chose the LM2678 for our 5 amp current needs for its high efficiency and reliably simplistic design. For the PCB design, I'll start off with discussing the power distribution system. Our architecture utilizes a 12-volt DC input which is routed to 3 dedicated voltage regulator PCBs. One regulator steps down this input voltage to 3.3 volts, supplying up to 1 amp to the MSP430 and pressure pad sensor. The next regulator outputs 5.2 volts, also up to 1 amp specifically for the optic sensors. The final regulator path leads to a 5-volt output, delivering up to 5 amps to support the Raspberry Pi, serving as one of the main processors demanding significant power load. Now let's take a look at the optic boards. These boards are designed to manage the proximity sensor as well as the break beam receiver and emitter sensors. By utilizing infrared technology, we achieve precise initial object detection, providing real-time feedback for the system. We have dedicated 5.2-volt power headers to provide a stable power source for consistent sensor performance. Once the sensors collect data, we also have transmission headers that output their signals directly to the GPIO pins of the MSP430 microcontroller. Finally, let's discuss the main board, which serves as the central hub of our system. We begin by adapting 12-volt DC input, which then powers the motor driver and our voltage regulation PCBs. The MSP430 microcontroller is routed to manage all peripheral sensors, the motor driver, as well as the communication lines to the Raspberry Pi 5. To ensure flexibility, we have an additional pin header for integrating extra GPIOs if necessary, as well as a ground pin header for easy troubleshooting. Starting off with the PCB layouts, we have the main PCB. Each separate PCB has a specified pin header connected to the main board, so we can easily troubleshoot later on. Starting in the top left, we have the 12-volt DC input, which will feed into our regulators, which are located in the center, spaced out for easy integration, along with the motor driver placed at the edge of the board for easy connection to the motor. The sensors, Raspberry Pi, and MSP430 are also well spaced out for efficient transmission of data and ease of troubleshooting. Displayed here are the PCB layouts for our voltage regulation. The figure on the left showcases both the 3.3 volts and 5.2 volts regulator boards, which share an identical layout and IC. The only distinction is the value of the R2 feedback resistor, which sets the desired output voltage. On the right is the 5-volt regulator PCB. This design accommodates for the significantly higher current demand, up to 5 amps for the Raspberry Pi. Both PCBs are equipped with pin headers for seamless connection to the main PCB. Additionally, critical components such as the input capacitors and feedback resistors are strategically placed as close to the regulator IC as possible. This follows best practices outlined by their respective datasheets. Next, we have the PCB layout for the optics proximity sensor. Here we have the 4-pin header that will connect to the main board. We made sure to have the bypass capacitors as close to the IC as possible. Finally, we have the sensors that will execute the initial detection and communicate with the MSP430. Here we have the PCB layout for our optics breakbeam emitter and receiver. Both boards feature 4-pin headers to interface with the main PCB. It follows the same layout principles as the proximity sensor. It will also communicate to the MSP430 as another set of detection for safety purposes.
For object detection, we compared 3 different models: YOLO, faster RCNN, and SSD. We needed a model that was well balanced between both speed and accuracy, while also running well on our Raspberry Pi 5. For these reasons, we chose to use the YOLO, or You Only Look Once model. This model is fast enough to complete inferencing in real time, while also having a high inferencing accuracy on the objects it detects. To handle object detection and classification, we chose to use YOLO version 11. After running this model on the Pi, we've seen successful detections of my cat Maple, as seen on the right, with an accuracy typically between 75 to 95%. The model currently runs inferences on between 2 to 2.5 frames per second, which is fast enough for our real-time detection needs. Converting to an NCNN format allows us to run the extra large weight file reliably, giving us the most accurate predictions possible. The YOLO family models come pre-packaged with easy methods for adding bounding boxes and labels around detected objects, And because we chose the no IR version of the camera module, our detection model can continue to work even in low light conditions. Moving on to the mobile app integration, we started by choosing a framework to build the app with. The frameworks compared were Flutter, React Native, Ionic, and Kotlin multi-platform. We chose to use Flutter as it has near-native performance while also having a very customizable UI using Flutter library widgets. To handle the hosting for the mobile app, we had 3 service considerations: Firebase, Heroku, and DigitalOcean. The most important factors here were how well the service scales with usage, its ease of setting up and usage, and pricing. We chose to use Firebase as the hosting service as it's very easy to use and free to start out with a small rising cost as the scale increases. As mentioned earlier, we chose to use Flutter as our app's framework, which is an open source software development kit created by Google. An important reason for choosing Flutter was how easy it is to quickly set up an app using the built-in widget library and UI themes. Flutter is also a multi-platform dev kit, meaning that it can support both iOS and Android in one single codebase. When debugging Flutter apps, we can also use its hot reloading feature to apply changes and fixes without even needing to restart the debugging window. For the hosting service, we chose to use Firebase, which is also owned by Google. We'll also be using Firebase to handle many of the back-end features. More specifically, we'll be using Firebase Authentication for handling logins and registrations, Firebase Firestore for storing user data, the activity log, and the status on favorited images, Firebase Storage for storing all the images that the Pi sends to the app, and Firebase Cloud Messaging for sending push notifications through the app. On startup, new users will be greeted with a splash screen with options for signing up for a new account or logging into an already created one. On the registration page, users are prompted to sign up with a valid email and password. After signing up, each user is given a randomized ID in Firebase for handling any back-end user-specific services. When logged into the app, users will have the ability to change their passwords. As previously mentioned, Firebase Authentication is used for handling both user signups and logins, as well as storing any registered user credentials. After logging in, a user will be taken to the home landing page. This page primarily serves as navigation to the other pages of the app, either through the toggleable side navbar or through the buttons on the home screen. In the gallery page, the app will display rows of images sent from the Pi whenever a cat or dog is detected, with a minimum time between pictures of 5 minutes. Images are sorted from newest to oldest and can also be filtered by a specific day with the calendar button in the top right. Users can favorite images or just simply delete them from here. Finally, in the activity log, the app will display a simple text page that shows any recent cat or dog detections with a timestamp of when the event occurred. Like the gallery page, these can also be filtered by a specific date.
Here we highlight the improvements made to our guard railing system. Our initial prototype, which used off-the-shelf metal rails, suffered from instability and excessive rattling. To address this, we designed a custom, more secure rail structure that allows the motorized door to open and close with significantly improved smoothness and stability. Here we show the complete hardware setup of the PAWS system. All electronic components have been securely housed within custom 3D printed enclosures, which are firmly mounted onto the wooden structure of the litter box for stability and protection. Here's the budget and bill of material breakdown for our project. The most expensive items include the fully enclosed structure, the Raspberry Pi, and the total order of 7 PCBs. Overall, we did go over our initial plans. However, right now we have all of the materials we need for the prototype. Let's go over the team's work distribution. I'm responsible for all optical and housing design. Kenza is handling all of MSP 430 programming with some contribution to the mobile app. Jeffrey is in charge of all power and PCB hardware, and Christian is handling all of the Raspberry Pi programming with the most contribution to the mobile app. All subsystems have been built and tested, and full integration of the breadboarded prototype is 100% functional. We are doing some final troubleshooting with the PCBs.